The morning of July 24th, 1943. Somewhere west of Truk Lagoon, in the sweltering waters of the Western Pacific, Lieutenant Commander Lawrence Randall Daspit stood hunched over the periscope of the USS Tinosa. Through the lens, framed perfectly in the crosshairs, sat 19,000 tons of Japanese steel, the Tonan Maru No. 3, one of the largest tankers in the Imperial Japanese Navy's fleet. She was alone, unescorted, making barely 10 knots. For a submarine commander in the middle of the Pacific War, this was the equivalent of finding a winning lottery ticket on the sidewalk. Daspit's crew had been alerted to the ship's route through decoded Japanese communications. They'd positioned themselves perfectly. Now, at 900 yards, he had a textbook shot. "Fire one," Daspit ordered. 30 seconds later, the sonarman's voice crackled through the con. "Hit, sir!" But no explosion, just a dull metallic thump that echoed through the submarine's hull, like someone had struck the side of a garbage can with a baseball bat. Daspit's jaw tightened. He'd heard that sound before. They all had. It was the sound of 685 pounds of high explosives that refused to explode. The sound of a torpedo that had travelled thousands of yards, struck its target dead center, and then nothing. A dud. But Daspit had more torpedoes, plenty more. He'd sink this ship if he had to empty every tube aboard Tinosa. Over the next hour and a half, Lieutenant Commander Daspit would fire 15 torpedoes at the crippled tanker. Only 2 would explode. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The failure wasn't unique to Daspit or to Tinosa. By the summer of 1943, nearly every submarine commander in the United States Navy's Pacific Fleet had filed similar reports. Torpedoes that ran underneath their targets, torpedoes that exploded prematurely, miles away from enemy ships, torpedoes that struck their targets with perfect accuracy and then simply stopped. Japanese vessels were reportedly limping into port with American Mark 14 torpedoes lodged in their hulls, unexploded, like giant metal slivers. The weapon that was supposed to win the submarine war in the Pacific had become, in the words of one historian, reliable only in its unreliability. And yet, for 18 months, the Bureau of Ordnance in Washington had insisted there was nothing wrong with the torpedo. The problem, they said, was with the submariners themselves. Poor training, improper maintenance, bad firing solutions, anything but the torpedo. But on that July morning in 1943, when Lawrence Daspit returned to Pearl Harbor with one remaining torpedo saved specifically for analysis, the fiction could no longer be maintained. The Mark 14 torpedo, America's primary submarine weapon, the result of over a decade of development and millions of dollars in investment, was fundamentally, catastrophically broken. And fixing it would require a renegade team of engineers, a heap of scrap metal from Japanese planes shot down at Pearl Harbor, and the kind of field testing that should have been done before the war even started. This is the story of how America's submarines fought the first half of World War II with a weapon that didn't work, and how one engineer's fatal fix conducted in defiance of Navy bureaucracy and at considerable personal risk finally gave American submariners a torpedo that could actually sink ships. To understand the magnitude of the failure, you have to understand what the Mark 14 was supposed to be. Development began in January of 1931, during the depths of the Great Depression. The Navy allocated $143,000 for its creation, a substantial sum at the time, though nowhere near what would be needed for proper testing. The Mark 14 was designed to replace the aging Mark 10 torpedo, which had been in service since World War I. At 20 feet 6 inches long, it was a sleek, steam-powered weapon capable of travelling over 5 miles at speeds approaching 53 miles per hour. Its warhead packed 643 pounds of TNT, later increased to 668 pounds of Torpex, an even more powerful explosive mixture. But the Mark 14's real innovation was its exploder mechanism, designated the Mark VI. This was no simple contact detonator that went off when it struck a ship's hull. The Mark VI combined two separate firing systems, a magnetic influence exploder and a backup contact exploder. The magnetic component was designed to detect changes in Earth's magnetic field caused by a ship's steel hull. The torpedo would run beneath the target, sense the magnetic disturbance, and detonate directly under the keel where there was no armor, no torpedo blisters, no defensive plating. The resulting gas bubble from the underwater explosion would, in theory, snap the ship's spine like a dry twig, breaking it in half. If the magnetic exploder somehow failed, the contact exploder would serve as backup, detonating when the torpedo actually struck the target's side. On paper, it was brilliant. In practice, it was developed under conditions that all but guaranteed disaster. The Great Depression had strangled military budgets. Naval funding from 1923 through 1934 averaged less than $350 million per year, with total personnel hovering around 110,000. Each Mark XIV torpedo cost approximately $10,000, roughly the same as a fighter aircraft airframe, without the engine, equivalent to about $171,000 today. That price tag made testing prohibitively expensive. You don't blow up $10,000 torpedoes just to see if they work, not when money is that tight. So the testing was minimal, criminally minimal. The magnetic influence exploder was developed in complete secrecy at the Naval Torpedo Station in Newport, Rhode Island. Project G-53, as it was designated, was created behind what one naval historian called the tightest veil of secrecy the Navy had ever created. The prototype was fitted to a Mark X torpedo and test-fired in Narragansett Bay on May 8, 1926. The submarine USS L-8 served as the target. In the first test, the torpedo ran underneath the target but didn't explode. The second test worked. Those two shots, were the only live-fire tests of the magnetic exploder conducted before World War II. Let that sink in. America's primary submarine weapon, the device that would be expected to sink thousands of tons of enemy shipping, had been live-fire tested exactly twice before the war started. And one of those tests had failed. The contact exploder wasn't much better. It relied on a firing pin mechanism that had to travel along guide rails when the torpedo struck its target. The pin would then strike a percussion cap, which would detonate the warhead. Simple enough. But the mechanism was designed during peacetime, tested in laboratory conditions, and never subjected to the kinds of high-velocity, high-angle impacts it would experience in actual combat. Dummy warheads much lighter than real ones were used for most tests to allow torpedoes to float when they ran out of fuel so they could be recovered. Nobody thought to test how the heavier combat warheads would affect the torpedo's performance. Nobody thought to fire torpedoes at actual ship hulls at combat speeds to see if the firing pin could withstand the impact. The tests that should have revealed these problems simply weren't done. Then there was the depth control problem. The Mark XIV was supposed to run at whatever depth the crew set, usually between 4 and 10 feet, shallow enough to strike beneath the waterline but deep enough to avoid detection. But the pressure sensor that controlled depth was positioned in the tail cone of the torpedo, where hydrodynamic effects created artificially low pressure readings when the weapon was moving. The torpedo's depth control engine would sense that low pressure, interpret it as being too shallow, and automatically trim the weapon to run deeper, much deeper. In actual combat conditions, Mark XIV torpedoes ran 10 to 11 feet deeper than set. If you aimed at a destroyer's waterline, your torpedo would glide harmlessly beneath its keel. But in static laboratory tests, torpedoes immersed in pools of still water, the depth gauge worked perfectly because there was no hydrodynamic flow to distort the reading. The problem was invisible until the weapon was fired in combat. These three flaws, depth control error, magnetic exploder hypersensitivity, and contact exploder failure, should have been caught during development. But the combination of budget constraints, peacetime complacency, and institutional secrecy created a perfect storm of inadequate testing. When the Mark 14 entered service, it was effectively an experimental weapon being fielded as frontline equipment. The submariners who would carry it into combat had no idea they were about to go to war with a weapon that had never been properly tested. December 7, 1941, Pearl Harbor. The day America entered World War II was also the day American submarines began discovering their primary weapon was broken. Within weeks of the attack, submarine commanders were filing reports of torpedo failures. Lieutenant Commander Frederick B. Warder, commanding officer of the USS Seawolf, was one of the first to document the problems. Over 6 war patrols, Seawolf fired dozens of Mark 14 torpedoes with dismal results. In one engagement near Christmas Island, Warder fired a spread of torpedoes at the Japanese light cruiser Naka from close range. One torpedo struck, and the cruiser limped away for repairs. On multiple occasions, Seawolf's crew heard explosions after firing, but saw no damage to enemy vessels. When Warder switched back to the older Mark 10 torpedoes, the very weapons the Mark 14 was supposed to replace, Seawolf's success rate improved dramatically. Other commanders reported similar experiences. Torpedoes that seemed to run true then exploded prematurely hundreds of yards from their targets. Torpedoes that disappeared beneath enemy ships without detonating. Torpedoes that struck targets with audible thuds that echoed through the submarine's hull but produced no explosions. The reports piled up at Submarine Command headquarters in Pearl Harbor and Fremantle, Australia. Something was catastrophically wrong. But when submarine commanders complained to the Bureau of Ordnance in Washington, they were met with skepticism, bureaucratic resistance, and sometimes outright hostility. The torpedoes were fine, Board insisted. The weapon had been extensively tested. If submarines weren't sinking ships, it was because their crews weren't properly trained or weren't maintaining the weapons correctly. In 1942, submarines in the 3 regional Pacific Ocean commands fired 1,442 torpedoes. They claimed to have sunk 211 ships, totaling almost 1.3 million tons. Post-war analysis of captured Japanese records revealed the true figures. 109 ships, totaling 41,871 tons. The Mark 14's failure rate was directly responsible for the gap. Submarines were getting into attack positions, exposing themselves to enemy counterattacks, firing weapons that should have been lethal and accomplishing almost nothing. Men were dying in depth charge attacks after torpedo runs that should have sunk their targets but instead merely alerted enemy escorts to the submarine's presence. 20 American submarines were lost before October of 1943. How many might have survived if their torpedoes had worked the first time? Enter Rear Admiral Charles A. Lockwood. In May of 1942, he became Commander, Submarines, Southwest Pacific Area, based in Fremantle, Australia. Lockwood was a career submarine officer, a hard-driving commander who gave full support to his squadrons and their crews. Unlike many flag officers, he actually listened when his submarine commanders reported problems. And by mid-1942, the torpedo complaints were too consistent, too detailed, and too credible to ignore. Lockwood decided to do something the Bureau of Ordnance should have done years earlier. He ordered proper field tests of the Mark 14. On June 20, 1942, at Frenchman's Bay near Albany, Australia, Lockwood's team rigged a fishnet in the water and fired a series of Mark 14 torpedoes through it from 850 yards. The holes in the net told the story. The torpedoes were running between 11 and 15 feet deeper than their set depth. Lockwood reported his findings to Washington. The Bureau of Ordnance disagreed on technical grounds, so Lockwood repeated the tests. Same results, torpedoes running 11 feet too deep. He again requested that Bureau conduct equivalent tests. Finally, on August 1, 1942, 8 months into the war, the Bureau of Ordnance confirmed that tests conducted at Newport corroborated reports that Mark 14 torpedoes were running 10 feet deeper than set. The depth problem was eventually addressed by relocating the pressure sensor from the tail cone to the mid-body of the torpedo, where hydrodynamic effects were minimized. By August of 1942, submarines could at least count on their torpedoes running at the correct depth. Hit rates improved, but the duds and premature explosions continued. Now the magnetic exploder came under scrutiny. Submarine commanders suspected the Mark 6's magnetic influence feature was the culprit. The Earth's magnetic field varies by location. It's stronger near the magnetic poles, weaker near the equator. The limited testing done at Newport, Rhode Island, hadn't accounted for these variations. In the tropical Pacific, where most submarine operations occurred, the magnetic field was different enough to cause the exploder to trigger prematurely. Torpedoes were detonating when they sensed the distant magnetic field of an approaching ship, exploding harmlessly hundreds of yards away. On April 9, 1943, Lieutenant Commander John A. Scott in the USS Tunney found himself in an ideal attack position against 3 Japanese aircraft carriers, Hio, Junyo, and Taiyo, at a range of just 880 yards. He fired all 10 torpedo tubes. 7 torpedoes exploded, the submarine crew celebrated, but not one of the carriers reduced speed. Later intelligence reports confirmed what Scott feared. All 7 explosions had been premature. The magnetic exploders had fired the warheads too early. The carriers sailed on, undamaged. The next day, USS Pompano attacked the aircraft carrier Shokaku, firing 6 torpedoes. At least 3 exploded prematurely. The carrier was not damaged. By this point, many submarine commanders were taking matters into their own hands. The Bureau of Ordnance had ordered that the Mark 6 exploder mechanism be sealed. Torpedo shop personnel applied dabs of paint to the screws holding the exploder to the torpedo body. Any tampering would mar the paint. But submarine torpedomen found matching paint, removed the exploders, deactivated the magnetic influence feature, and carefully repainted the screw heads. When the torpedoes were returned to the shop, there was no way to tell they'd been modified. It was an open mutiny, conducted with paintbrushes and wrenches in the cramped torpedo rooms of submarines half a world away from Washington. Finally, in late June of 1943, Admiral Chester Nimitz, Commander-in-Chief of the Pacific Fleet, ordered all submarines in his command to deactivate the magnetic influence exploders. Use contact exploders only. The magnetic feature, after years of development and all that secrecy, was being abandoned, but the nightmare wasn't over. July 7, 1943, USS Tinosa, under Lieutenant Commander Lawrence Darspit's command, departed Midway Atoll for her second war patrol. Her assigned area, the sea routes between Borneo and Truk Lagoon. By this time, the depth control problem had been fixed. The magnetic exploders had been deactivated. Darspit and his crew had every reason to believe their Mark 14 torpedoes would finally work as advertised. 17 days later, at dawn on July 24th, Tinosa's radar picked up a contact. Through the periscope, Darspit identified it as a large tanker later confirmed as the Tonan Maru, No. 3, a 19,000-ton whale factory ship that had been converted to an oil tanker. She was alone, making just 10 knots, carrying precious fuel from Palau to Truk. Codebreakers had alerted Tinosa to the ship's route. Now she was framed perfectly in the crosshairs. At 5:55 in the morning, Darspit began his attack. He fired 4 torpedoes from 4,000 yards. 2 struck the target and exploded. The sounds echoed through Tinosa's hull, 2 solid hits. Smoke poured from the tanker's port quarter. She stopped, listed to port, settled by the stern. Darspit moved in for the kill. At 9:30, he fired again from the starboard side. The torpedo hit. The sonarman heard it strike, but no explosion, just that hollow metallic thump. Darspit tried again. Same result, hit, no explosion. By 10:30, he'd fired 7 torpedoes. Only the first two had exploded. Daspit approached to point-blank range, 875 yards, square off the target's beam. A textbook firing position. He fired the 8th torpedo at 10:11, hit, no effect. The 9th torpedo at 10:25, hit, no effect. The 10th torpedo at 10:40, hit, no effect. At 10:48, Daspit fired his 11th torpedo. In his patrol report, he recorded what happened next. This torpedo hit well aft on the port side, made a splash at the side of the ship, and was then observed to have taken a right turn and to jump clear of the water about 100 feet from the stern of the tanker. I find it hard to convince myself that I saw this. He fired 4 more torpedoes, numbers 12, 13, 14, and 15. All struck the target. None exploded. By 11:30, a Japanese destroyer had arrived and begun dropping depth charges. Daspit took Tinosa deep. In his log, he noted, had already decided to retain 1 torpedo for examination by base. He'd fired 15 torpedoes at a stationary target under ideal conditions. 15. Only 2 had exploded, and those had been fired at oblique angles. The 13 torpedoes fired in textbook fashion, striking the target at 90 degrees, had all been duds. Tinosa arrived at Pearl Harbor on August 4, 1943. The submarine tied up at the pier, and Lieutenant Commander Daspit, still seething with frustration, made his way directly to the headquarters of Commander, Submarines, Pacific Fleet. Rear Admiral Charles Lockwood was waiting. Lockwood later wrote about that meeting. I expected a torrent of cuss swords damning me, the Bureau of Ordnance, the Newport Torpedo Station, and the base torpedo shop, and I couldn't have blamed him. 19,000-ton tankers don't grow on trees. But Daspit didn't curse. He was too professional for that, and too furious. Instead, he calmly, methodically recounted what had happened. 15 torpedoes, 2 explosions, 13 confirmed hits that produced nothing but metallic thuds. A 19,000-ton tanker that should have been at the bottom of the Pacific, still afloat, still steaming, still carrying fuel to Japanese bases. Daspit had brought back the 1 remaining torpedo, carefully preserved, for Lockwood's team to examine. Lockwood listened to Daspit's report and felt the weight of 18 months of failure settle on his shoulders. The depth problem had been fixed, the magnetic exploder had been deactivated, and still the Mark 14 was failing. There was only one component left to investigate, the contact exploder itself. The problem was proving it. When Lockwood's torpedo shop examined Daspit's remaining torpedo, they found nothing obviously wrong with it. The exploder looked fine. The firing pin mechanism appeared to be in working order. But laboratory inspections of intact weapons weren't revealing the problem. What Lockwood needed was to examine a torpedo that had actually failed to explode after striking a target. He needed to see what happened to the firing mechanism under combat conditions, and that meant doing something the Bureau of Ordnance had never done, conducting live fire tests that replicated actual combat impacts. For this, Lockwood turned to one of the most innovative officers in the submarine force, Captain Charles Bowers Mommsen, nicknamed Swede. Mommsen was already a legend in the Navy. In 1939, he directed the rescue of 33 crew members from the sunken submarine USS Squalus off Portsmouth, New Hampshire, using a diving bell he'd helped develop. He'd invented the Mommsen lung, a portable breathing device that had saved hundreds of submariners from sunken vessels. He was the father of the submarine rescue chamber that had become standard Navy equipment. But beyond his technical brilliance, Mommsen possessed something equally valuable. He was willing to challenge official Navy doctrine when he knew it was wrong. His outspoken habit of going against the official grain had earned him few friends in the Pentagon, but it had also earned him the trust of men like Lockwood, who valued results over politics. In the summer of 1943, Mommsen was commanding Submarine Squadron 2 at Pearl Harbor. His skippers were the ones filing the dud reports. They were the ones returning from patrol with empty bags and full torpedo rooms, frustrated beyond measure at having to carry useless weapons into enemy waters. Mommsen knew the contact exploder had to be defective. He just had to prove it. He began by studying charts of the waters around the Hawaiian Islands, looking for a specific geological formation, sheer vertical cliffs that went straight down into deep water with a sandy bottom. Such a location would allow a torpedo to be fired at the cliff face, strike it as if it were hitting a ship's hull, and then fall to a depth where it could be recovered if it failed to explode. He found what he needed off the coast of Kahulaw, a small, uninhabited island about 7 miles southwest of Maui. The island had vertical cliffs rising directly from water deep enough for torpedo testing but shallow enough for recovery operations. On August 31st, 1943, Mommsen's team began firing live Mark 14 torpedoes at those cliffs. The submarine USS Muskellunge served as the firing platform. Art Taylor, ComSubPAC's gunnery and torpedo officer, supervised the tests. They fired the first torpedo. It ran true, struck the cliff, and exploded. Good. The torpedo worked as designed. They fired a second torpedo. It ran true, struck the cliff, and nothing. No explosion. Just a dull thud as 685 pounds of Torpex-filled warhead collided with solid rock and failed to detonate. The torpedo sank to the seabed, 50 feet down. Now comes the dangerous part. That torpedo contained a live warhead, 685 pounds of high explosive, and a firing mechanism that had already demonstrated it was unstable. One wrong move during recovery could detonate the weapon, killing everyone nearby. Mommsen didn't hesitate. He grabbed his diving equipment, jumped into the Crom, water, and swam down to the torpedo himself. He located it on the sandy bottom, secured a line to it, and supervised as the crew gingerly hoisted the live weapon onto the deck of the service ship Widgeon. Then, with the same calm precision he'd shown during the Squalus rescue, Mommsen personally disassembled the exploder mechanism while it was still attached to the live warhead. What he found was both simple and damning. The firing pin had not struck the percussion cap with enough force to cause detonation. In fact, it looked like the pin hadn't moved much at all along its guide rails. The mechanism appeared to have jammed on impact. But why? The Mark 6 contact exploder used a firing pin that travelled perpendicular to the torpedo's direction of travel. When the torpedo struck a target, the sudden deceleration should have caused the firing pin to slide forward along its guide rails, strike the percussion cap, and detonate the warhead. But, at high impact speeds, the torpedo was travelling at 46 knots when it hit. The forces involved were enormous. The firing pin and its housing were being subjected to deceleration forces equivalent to 500 times the force of gravity, with a frictional component of 190 pounds pressing on the guide rails. At a perfect 90-degree impact angle, the kind of shot submarine commanders had been trained to make, the firing pin mechanism was simply crushing under the load. The guide rails would bend, the firing pin would jam, and the torpedo would fail to explode. The bitter irony was now clear. The better your shot, the more likely your torpedo would fail. A perfect broadside hit at 90 degrees, the textbook attack angle drilled into every submarine officer produced enough impact force to jam the firing mechanism. Only glancing blows, the kind that occurred when torpedoes struck at oblique angles, reduced the forces enough to allow the firing pin to function. That's why Daspit's first 2 torpedoes against the Tonan Maru had exploded. They'd hit at awkward angles during his initial pursuit. The 13 subsequent torpedoes, fired from perfect positions at right angles to the target, had all jammed on impact. American submarine commanders had been taught that the ideal firing solution would produce the best results. In reality, ideal firing solutions were producing duds, but Mommsen needed more evidence. Firing torpedoes at cliffs was expensive and dangerous, and it could only test one torpedo at a time. He needed a way to replicate the impact forces more safely and more quickly. He found his solution in a cherry-picker crane at the Pearl Harbor submarine base. If you filled a torpedo warhead with sand to simulate the weight of explosives, fitted it with a live Mark 6 exploder, and dropped it from a height calculated to match the impact velocity of a 46-knot torpedo. You could test the exploder mechanism without actually firing torpedoes or risking premature detonation of live warheads. Mommsen's team calculated that a drop from 90 feet would produce impact forces roughly equivalent to a torpedo striking at 46 knots. Working under the supervision of Art Taylor, a naval reserve officer named E.A. Johnson conducted the drop tests. They rigged up the cherry picker, hoisted dummy warheads filled with sand to 90 feet, and dropped them onto a steel plate positioned at different angles to simulate various impact angles. They tested 10 warheads. 7 failed to explode. 70% failure rate. When they disassembled the duds, they found the same problem Mommsen had discovered in the cliff test. The firing pins had jammed along their guide rails under the impact forces. The mechanism simply wasn't rugged enough to withstand the deceleration forces of a high-speed, perpendicular impact. In 7 out of 10 tests, the firing pin either bent, crushed, or failed to travel far enough to strike the percussion cap. The problem was now undeniable. The Mark VI contact exploder had a fundamental design flaw that made it prone to failure precisely when it should have been most reliable. This information was passed to the Bureau of Ordnance in Washington, along with detailed documentation of the testing. Board's response was to suggest using a stiffer spring, the same fix that had been tried decades earlier with previous torpedo designs. But Lockwood wasn't waiting for Washington anymore. His submarines were going to war every day with weapons that didn't work. Men were dying because of bureaucratic inertia. If Buord couldn't or wouldn't fix the problem, Lockwood would fix it himself. The solution, it turned out, was elegantly simple. Make the firing pin lighter. If the firing pin had less mass, it would be subject to less inertial force during impact. The guide rails wouldn't have to withstand as much pressure, the mechanism wouldn't jam, but you couldn't just file down the existing steel firing pins. They needed to be completely redesigned and manufactured from a lighter material. The machine shop at the Pearl Harbor submarine base needed lightweight aluminum alloy, and they needed a lot of it. They found their material in the most ironic source imaginable: the wreckage of Japanese aircraft shot down during the attack on Pearl Harbor on December 7, 1941. When the Japanese struck Pearl Harbor, several of their planes were shot down over the island. In the chaos of the attack and the immediate aftermath, nobody had thought much about the downed aircraft beyond clearing them away. But now, nearly 2 years later, those wrecks became invaluable. The engine from one Japanese fighter, melted down, provided the initial batch of lightweight aluminum alloy needed for the new firing pins. The metal was machined into lighter firing pin assemblies with reinforced guide tracks. The new designs were tested using the cherry picker method. They worked. The lighter firing pins traveled along. Their guide rails, without jamming, struck the percussion caps with sufficient force and detonated the practice warheads reliably. But one Japanese fighter engine wouldn't provide enough metal to refit the entire Pacific Fleet's submarine force. Mommsen's team needed more aluminum alloy, and they needed it fast. They found another source at Hickam Army Airfield, just a few miles from the submarine base. Aircraft propellers had to be both light and strong. They were made from aluminum alloys that were perfect for the new firing pins. When Mommsen's team approached Army Air Forces personnel and explained they needed every damaged propeller they could find, one officer supposedly replied, "A better use for a busted prop could not be found anywhere." Damaged propellers from Army aircraft were collected, melted down, and machined into firing pin assemblies. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The work was done at the submarine base itself, bypassing the normal channels that would have required Bureau of Ordnance approval. Lockwood had learned from the depth control disaster and the magnetic exploder debacle that waiting for Washington meant more failed patrols, more missed opportunities, and more American deaths. He wasn't going to make that mistake again. Every machine shop at the submarine base was put to work fabricating the new firing pin mechanisms. Lockwood personally insisted that every single new exploder be tested and proven perfect before being installed in torpedoes. There would be no more assumptions, no more hoping the weapons would work. Each exploder had to demonstrate reliability before it went to sea. By late September of 1943, the first submarines began leaving Pearl Harbor with torpedoes fitted with the new contact exploders. The USS Barb departed on September 30th with 20 torpedoes, all equipped with modified firing pins. Other submarines followed. The results were immediate and dramatic. The USS Haddock, one of the early boats to receive the modified torpedoes, sank 2 Japanese ships with 4 torpedo hits. No duds, 4 hits, 4 explosions, 2 ships sent to the bottom. Other boats reported similar success. The dud rate, which had been as high as 70% in some patrols, dropped below 10%. American submarines were finally armed with reliable weapons. Meanwhile, the Bureau of Ordnance in Washington had been working on their own solution. Instead of lighter firing pins, Buord developed an entirely different mechanism, a ball switch and electric detonator that eliminated the firing pin mechanism altogether. When the torpedo struck a target, the impact would cause a small ball bearing to roll along a track, completing an electrical circuit that would fire the detonator. No firing pin, no guide rails, no jamming. It was a more elegant solution, and it eventually became the standard design. The first torpedoes with the new electric detonators were sent to sea in September of 1943, the same month Pearl Harbor's modified firing pins reached the fleet. But it was Momsen's work and Lockwood's willingness to bypass official channels that gave American submariners working torpedoes first. After 21 months of war, historian Clay Blair Jr. wrote, "The 3 major defects of the Mark 14 torpedo had at last been isolated. Each defect had been discovered and fixed in the field, always over the stubborn opposition of the Bureau of Ordnance. 21 months. That's how long American submarines fought with fundamentally broken weapons. From December of 1941 to September of 1943, American submariners went into combat, knowing their torpedoes might run too deep, might explode prematurely, or might fail to explode at all, even when they struck their targets perfectly. The human cost is impossible to calculate. Precisely. Of the 53 American submarines lost in World War II, 20 were sunk before October of 1943. How many of those boats might have survived if their torpedoes had worked properly? If a submarine's first attack had sunk its target instead of merely alerting enemy escorts to its presence? If boats hadn't had to make multiple attack runs because their initial torpedoes failed? We'll never know. But we know this. Dozens of war patrols were wasted. Hundreds of American lives were lost. Thousands of tons of enemy shipping warships, transports, tankers sailed on undamaged because the weapons meant to sink them were defective, and the institutional failure went beyond the torpedoes themselves. The Bureau of Ordnance had been warned. In 1939, before the war even started for the United States, the Newport Torpedo Station reported that the magnetic influence exploder was suffering from unexplained premature detonations. A physicist was brought in to investigate. He uncovered 4 sources of prematures and reported that the engineers at Newport weren't employing proper tests. Nothing was done. When submarine commanders began reporting torpedo failures after Pearl Harbor, they were told the problem was with their seamanship, not the weapons. When Lockwood conducted his net tests in June of 1942, proving the depth control was faulty, the Bureau of Ordnance initially rejected his findings. When magnetic exploder failures mounted, Buord defended the design and blamed atmospheric conditions or improper use. At every stage, the institution chose to defend its reputation rather than fix the weapon. This pattern of denial had consequences beyond the Mark 14. In July of 1943, after Admiral Nimitz ordered all submarines in his Pacific Fleet Command to deactivate the magnetic exploders, one area commander refused to comply. Admiral Ralph Christie commanding submarines in the Southwest Pacific area, based in Fremantle, Australia, had been the officer in charge of testing the magnetic exploder during its development in the 1930s. He'd invested years of his career in that weapon. He couldn't accept that it was fatally flawed. Christie ordered his boats to continue using the magnetic influence feature. When submarine captains in his command questioned the Mark 14's reliability, Christie transferred them out. Word spread quickly. Questioning the torpedo in Christie's command was a sure way to be assigned to shore duty. It wasn't until November of 1943, when Vice Admiral Thomas Kincaid arrived as Christie's new superior, that Christie was given a direct order to deactivate all magnetic exploders. By that time, Christie's submarines had wasted months of patrols with weapons that didn't work, but once the fixes were implemented, the Mark 14 became the weapon it should have been from the start. From September of 1943 through the end of the war, American submarines equipped with reliable torpedoes devastated Japanese shipping. By August of 1945, American submarines had sunk 1,178 Japanese merchant vessels, totaling 5,053,491 tons. That's roughly 55% of Japan's total merchant marine capacity. The submarine campaign severed Japan's supply lines for oil, raw materials, and food. Industrial production collapsed. Military operations were hampered by lack of fuel. Troop reinforcements couldn't reach combat zones. The Allied blockade, powered by American submarines firing torpedoes that actually worked, contributed directly to Japanese naval defeats at battles like Leyte Gulf and forced resource rationing that undermined the entire Japanese war effort. The Mark 14 also sank significant Japanese naval units. The submarine USS Archerfish used Mark 14 torpedoes to sink the carrier Shinano, the largest warship ever sunk by a submarine. Dozens of cruisers, destroyers, and escort vessels fell to American torpedoes in the war's final 2 years. The weapon that had been a source of frustration and rage for 21 months became one of the most effective anti-shipping weapons of the war. It remained in service in the United States Navy until 1980, nearly 40 years. After the war, the best features of the Mark 14 were combined with technology captured from German torpedoes to create even more advanced weapons. For the men who fixed it, recognition came slowly. Captain Swede Mommsen received the Legion of Merit for his work on the torpedo problem. The citation noted his successful efforts at discovering and fixing the exploder defect that had plagued the submarine fleet for a year and a half. Lockwood was later promoted to Vice Admiral and continued commanding submarine forces in the Pacific until the war's end. But neither man forgot how close the Navy had come to fighting the entire war with defective weapons. In Lockwood's post-war writings, his frustration with the Bureau of Ordnance remained palpable. At one point, during a 1943 submarine officers' conference, he'd said, "If the Bureau of Ordnance can't provide us with torpedoes that will hit and explode, then, for God's sake, get the Bureau of Ships to design a boat hook with which we can rip the plates off a target's side." The torpedo scandal also prompted soul-searching about how the Navy developed and tested weapons. The Mark 14's problems had been predictable and preventable. Proper testing during development, not laboratory tests with dummy warheads, but live-fire tests under combat conditions, would have revealed all 3 major defects before the war started. The secrecy surrounding the magnetic exploder's development had prevented outside experts from reviewing the design and catching obvious flaws. The institutional arrogance that led Buord to blame submarine crews rather than investigate. The weapon itself had prolonged the crisis by more than a year. These lessons weren't lost on the Navy's leadership, though applying them consistently would remain a challenge in subsequent decades. As for Lieutenant Commander Lawrence Daspit, the man whose frustrating encounter with the Tonan Maru had provided the final, undeniable proof that the contact exploder was defective, he returned to combat with properly functioning torpedoes. Tinosa completed 12 war patrols during World War II and was credited with sinking 16 enemy ships, totaling 64,655 tons. She received 9 battle stars and Presidential Unit citations for her 4th, 5th, and 6th patrols. Daspit was promoted to full commander and later received the Navy Cross for his service. But the memory of that July day in 1943, 15 torpedoes, 2 explosions, 1 escaped tanker stayed with him. In some ways, his greatest contribution to the war effort wasn't the ships he sank, but the one that got away, because that failure, documented in meticulous detail in his patrol report, finally broke through the bureaucratic resistance and forced the Navy to confront the truth about its primary submarine weapon. The Tonan Maru No. 3, incidentally, survived Daspit's attack and limped into Truk Lagoon for repairs. She continued serving as a tanker for the Imperial Japanese Navy through the rest of 1943 and into 1944. But on February 17, 1944, during Operation Hailstone, the massive American carrier raid on Truk, she was finally sunk by dive bombers and torpedo aircraft from Task Force 58. The ship that had survived 15 American submarine torpedoes went to the bottom under aerial attack. She was later refloated by Japanese salvagers in 1951 and scrapped. In a sense, she outlasted the war itself, surviving both the torpedo that didn't work and the war that followed. The story of the Mark 14 torpedo is ultimately a story about the gap between design and reality, between laboratory conditions and combat conditions, between what should work in theory and what actually works when lives are on the line. It's a story about institutional failure, how bureaucratic pride, secrecy, and inadequate testing can turn an innovative weapon into a deadly liability. But it's also a story about the men who refused to accept failure, who risked their careers and their lives to prove the weapon was defective and to fix it themselves when the official channels failed them. Men like Lockwood, who ordered unauthorized tests, like Momsen, who dove into the water to retrieve a live torpedo that everyone else was afraid to touch, like the torpedo shop workers who found matching paint to hide their unauthorized modifications, like the submarine commanders who kept filing reports even when they were told the problem was their fault. And perhaps most importantly, it's the story about the cost of not testing systems properly before committing them to combat. The Mark 14 torpedo cost approximately $10,000 per unit in 1942 dollars. That expense seemed prohibitive during the Depression, leading to minimal testing. But the cost of fielding an untested weapon proved far higher. 21 months of failed patrols, hundreds of American lives, thousands of tons of enemy shipping that survived to fight another day, and the incalculable strategic cost of fighting the first half of the Pacific Submarine War with one hand tied behind America's back. Systems need to be tested the way they'll be used. Inadequate testing of complicated systems will almost inevitably lead to catastrophic problems when those systems are needed most. The Mark 14 torpedo proved that lesson in the most painful way possible. By September of 1943, American submarines finally had the weapon they'd needed since December of 1941. The depth control worked, the magnetic exploder was gone, and the contact exploder, fixed with firing pins made from the melted-down propellers of enemy aircraft, detonated reliably whether the torpedo struck at 90 degrees or 45 degrees or any angle in between. The engineers at Pearl Harbor, working with scrap metal and determination, had accomplished what the Bureau of Ordnance failed to do for 21 months. They'd made America's torpedoes actually explode. Thank you for reading. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.